is one of the simulated total dissolved phosphorus export. This is the additional module to the cold region hydrologic model. And also we have expertise on the groundwater modeling. It's the recharge from the cold region hydrologic model, and we incorporate it into the mod flow. And this is a kind of a 3D of the Oaks Aquifer in the south of the state. This is the Department of Water Resources project. We're looking at the science-based water appropriation for the irrigation from the Oaks Aquifer. So that is kind of the brief of our centers. We also do a lot of outreach, particularly hydrology education outreach to the Native American tribal college student and the high school student. So today's presentation is a compilation of my graduate student work, and you will see the citation of the work at the beginning. So it means that that particular graduate student is the lead author for that work. So a brief introduction of the Devils Lake Basin is the 10,000 square kilometer basin approximately located in North Dakota, in the central North Dakota. And the digital elevation model is pretty much straightforward. Lake water accumulated in the southern part of the basin, and from the north and west and the southeast, the water flows and accumulate toward the potholes and depression at the end goes to the chains of lake. This is the kind of a stream network in the Devils Lake Basin, and the land use land cover, mostly agricultural basin with a very dense population of the wetland on the eastern part of the basin. And the western part is little bit large water bodies with less wetlands and also more agricultural dominated. And we also have some herbaceous land use over here. Some of the issues on the water resources concerned in the Devils Lake Basin is the flooding is the one. I think it costs almost over $1 billion of the taxpayers for the flood mitigations and other issues in the Devils Lake region. And this is basically wetting under a warming and cooling phases are responsible for this huge amount of water influx in this terminal lake basin. It caused hydrologic changes. It caused the more nutrient to be exported in the lake. So Devils Lake experiences a wet climatic conditions since 1993, significant impacts on water resources. Like I said, the billions of USD, billions of dollars for the tax flood damages. And wetland surface area evaluation here is poorly understood. And we need to understand these lakes and the lake hydrology and wetland hydrology to effectively looking at the mechanism of hydrologic change. This is a 1999 Landsat images of the Devils Lake Basin. We quantified the water area to be 442 square kilometer, which is 4.4% of the entire watershed. And then fast forward 11 years, it doubles. So if you see here, the Lake Alice and Irvine barely exist here. And in 2002, they started to appear, and also some of the larger water body in the western part of the Devils Lake Basin started to appear. And 2011 was one of the highest wet condition in Devils Lake Basin. You see now 20% or 21% of the entire Devils Lake Basin is underwater. And then in 2027, it kind of recesses back a little bit in this it be due to the drier conditions. So you see that there is a huge increase in the surface water area and huge loss of farmland around the Devils Lake Basin since 1990. This is the kind of the historical lake level. We kind of went through a century-long dry spell before this wetting started in 1990, and the Devils Lake level started going up and up. One of my student, Alexis Archambault, she looked at the total water area changes since 1990 to see the total water area kind of going up pretty rapidly, and then started to fluctuate a little bit. And then it started going up again in 2009 and goes all the way to 2013. Now it recesses back a little bit. And we all know there are 3 outlets of the Devil's Lake was constructed in around this 2009 and 2010 period. So that helps, and also a dry condition and the higher summer evaporation started to pull it back a little bit. In the permanent water area, which is kind of a it is pretty responsive to the precipitation change. Plus, also like it is a it responds pretty slowly. So you see that permanent water area bodies kind of started to going up, and kind of settle down and go up, basically form the following the total water area. Whereas the seasonal water area kind of highly fluctuating, right? It is these are basically smaller water bodies. It's go up and down. It's kind of high frequency fluctuations in the Devils Lake area. And if you see, these red colors are basically the snowfall, and the blues are the rainfall. It's the snowfall kind of amount increases in early 90s. And we kind of do some of the change detections of those maps. And from 1990 to 1999, you see that quite a bit of bare land, those dark blues, are converted to a permanent water area. And then also some of the seasonal water bodies become permanent water bodies, and some of the bare land become the seasonal water area. So those are the changes are pronounced in first 9 years since 1990. And 2000 to 2003, the fluctuation is not there. It was a kind of called cold prairie drought. So you don't see a lot of exciting phenomena in the Devils Lake Basin. And 2004 to 2013, I call it a second wet phase, and we started to see more blues there. There's like conversion to the water area change. And these blues again that causing the second round of chain of lake expansion in the Devils Lake area. And 2014 to 2018 again, so we started to lose some of the seasonal and permanent water area around the Devils Lake region. And then this is the kind of a total water area change over the 29 years from 1990 to 2018. Again, we see the prominent new water area expansion of the large lakes, and the formation of the new permanent water bodies are seen pretty clearly. Now, why this climate flooding is happening around the Devils Lake Basin? We looked at the climates of the 1990 to 2004. And this is the average annual temperature. And you see that from 1990 to 96, it drops by 4 degrees. So we call it as a kind of a cooling phase. So 96 onward, there's another slightly warming phase, and again, another kind of a cooling phase going on. While the temperature is fluctuating through a series of cooling and wetting conditions, our precipitation was rising. This is the total precipitation was rising from 1991 all the way to 1999 before the prairie drought started in early 2000. But this rise of precipitation and these fluctuations of this particular first 7 years of cooling conditions is basically cause or trigger that particular rise of the Devils Lake from 1990 to 1997. I also plotted the average winter temperature and average summer temperature, and both are showing the similar patterns of the cooling and followed by the warming and the further cooling going on here. We split them, the precipitation and the snowfall and the rainfall, and both are showing in 90s of the high precipitation or the high snowfall and the or increasing snowfall and increasing rainfall pattern. We try to model this thing through a physically based cold region hydrologic model in a headwater basin that draining to the Lake Alice is called Mahmood Basin. Brief intro to the introduction to the cold region hydrologic model. It was developed by the researcher and scientist in the University of Saskatchewan. I was one of the postdoc in that group before I joined the University of North Dakota. It's a physically based model, and it's also a distributed model. It takes care of the snow processes, blowing snow transport, frozen and frozen and unfrozen soil infiltrations, and also the sublimation, canopy or intercepted snow sublimation, and in-transit sublimations. And at the end, the water being routed through the HR hydrologic response unit to the channel to the outlet basin. It has been tested in the cold region, in the mountains and the prairie across the world. So when we went to the Mahmood Basin, we collected a lot of snow water equivalent data. So we went out to the field using our snow tube. We collected snow data, and we kind of modeled that against the using the cold region hydrologic model. This particular site is located in this part of the Mavekuli Basin, and this is the simulated snow water equivalent, the blue line, and the red line you see cumulative snowfall. So you see the simulated snowwater equivalent and observed snowwater equivalent is higher than the cumulative snowfall. It means that the snow blows into this particular agricultural field and add more snow over there. But however, it's not the case all the time. Here you see the simulation and the observation is slightly lower than the cumulative snowfall. So snow probably blows out from the system. So those are the kind of the phenomena that the cold region hydrologic model can provide. We ran this model over last 30 years in the Mavekuli Basin. Again, this is where the Mavekuli Basin is. And this is the streamflow simulation model versus observation from 1990 to 2004, simulated by my graduate student Wenti, and 2004 to 2017, simulated by the Diane Van Hoy. This work is published in Water Resources Research. This is under submission to the Water Resources Research again. So you see that there is a huge hydrologic change since 1990, and there is a stream flows are increasing all the way to 97 to 90, all the way to 1997. There's a slight hiatus or low stream flow in the prairie drought conditions. Again, the stream flow is increasing all the way to 2011 in the in the Mavekuli region. So this hydrologic change is one of the major explanation of the all the lake area expansion in the Devils Lake Basin. We also looked at the hydrologic fluxes in Q over P, stream flow over precipitation ratio, and vertical flux or ET plus sublimation over precipitation ratio. And here we plotted 1991 to 2004. You see that 91, 92, 96, 94, 93, this early 90s basically cooling and wetting period, and Q over P or runoff ratio are in steady state. So it means that you are increasing precipitation and you are cooling the temperature or temperature dropping at that under that condition or under that climatic state, the runoff ratio are in steady state. But when we went to that warming and wetting phase, it became a transient condition and started to go toward this particular the high runoff ratio in that time. It's 97, 99 of those kind of flood year in the Devils Lake or high expansion of the lake area over there. In the prairie drought condition, they kind of clustered into low variation of the Q over P and the vertical flux over P. On the other hand, when we fast forward to this century, it has a two pronounced factor. One is like vertical flux dominated system in the after 2011. All these years 17, 14, 16. This is basically vertical flux dominated system, lesser of a slightly less precipitation, but more evaporation in this period. But before 2011, it is basically lateral flux or Q over P dominated system and a pretty high Q over P in this area. So this high Q over P, high Q over P are also responsible for the expansion of the chain of lakes over there. Some of the stream flow generation mechanism, we looked at some of the major flood or stream flow event of 1997, contributing area versus model stream flow. You see the kind of, and the blues are basically rising limb of the hydrograph and the red are recession limb. You see that it takes a while in the Mavekuli Basin to connect the entire system and start triggering the stream flow at the outlet. So it takes like almost like 40 to 50 hours in 1997 before actual flood pulses start to come in the Mavekuli Basin outlet and then start to recess back there. So here we kind of find a counterclockwise hysteresis loop by plotting the fractional contributing area and the stream flow. And these are the phenomena we are observing across the major runoff event in the at the outlet of Mavekuli Basin. They're kind of sharp increase in the stream flow while it is recessing because of the rainfall event in the spring rainfall event, it kind of sharply connect the stream flow area, and sometimes also rain on snow event kind of increase the connectivity of the Mavekuli Basin. Now I'm going to the nutrient concentration and export to dry and wet years. We try to understand that how the nutrient concentrations looks like and that water going to the Devil's Lake, and again we are again looking at the nutrient concentration in the Mavekuli Basin. This work is from my graduate student Tyson Jenop's master's thesis work. It's published in Journal Hydrology in 2020. And as we all know that the hydrology increases the nutrient, the more nutrient are exported to the lake through the stream flow and the runoff from the agricultural fields. There are some of the algae bloom warning across the Red River Basin, but the majority of lakes are experiencing the algae bloom. In particularly during the wet years when the large nutrient was exported to their lakes. Here we're looking at the two headwater basin that drain to Devil's Lake. One is the Mavekuli Basin. We have a USGS gauge at the Mavekuli USGS gauge there. Another is the Trip 3, where this is located, and it's also merging with the Mavekuli at the end and draining to Lake Alice. Again, the basic land use land covers are agricultural land and the herbaceous wetland and the grassland over there, and they're part of the northern Black Prairie and on the Drift Plain ecoregion, and the Turtle Mountain is on the northwest corner of the area. This is how the landscape look like from our when we are in the field. 2017, we call it 2016, 2017, that a wet year, the high snow accumulations and we observe like lots of heavy stream flow gush when we are in the field, and there and this is how the landscape look like in the 2027 and the wet winter year. And 2020 2018 or 27 2018, that is we consider as a hydrologically dry year. Everything was pretty, the snow accumulation was not high or very much lower than the average snow accumulations, and we don't see a lot of flow in the both stream flow outlet. We went there and collect the snow data and the snow water chemistry using the prairie snow tubes. And we also collect the water sample. This is one of the geopump and collecting the samples, and we pump it and filter the water in the infield conditions. And we also collect the soil samples for the Olsen phosphorus concentration. We did the water chemistry analysis in the UND's R lab and the soil chemistry analysis in the AgVice laboratory in Northwood, North Dakota. This is the wet year looks like. If we look at one of the stream condition, see that the water is going pretty fast in the in the 2017 stream flow, 2017 spring stream flow events. I'm talking about this particular stream flow event. And we also collect the phosphorus concentration. We also measured the phosphorus concentration. Our sampling is 3 times per day. We take it, one is the early morning and the midday around noon or 1 p.m. and also the somewhere in the late afternoon 4 to 5 p.m. So we don't want to miss any part of the hydrograph when we are sampling from these two outlet gauges in the Trip 3 of them in the Mavekuli Basin. On the other hand, 2018 was pretty dry year, and the same location was gushing water so hard, so fast in 2017, and it is barely actually moving at that time. And the stream flow was much, much smaller. If you that goes only 10 cubic meter per second compared to the 80 cubic meter per second in 2017. So one is the hydrologically dry year, another is the hydrologically wet year. And we looked at these 2-year comparisons, the dry versus wet. The total phosphorus concentration in the Trip 3 and the Mavekuli Basin is much lower in the wet year. and the much little bit higher in the dry year. And we believe that the dilution is one of the reason that phosphorus concentration is lower in the wet year, and we might have a limited supply, or the way the water is coming, the rate the water is coming from the different headwaters of the Maviculi Basin, the source of phosphorus is not increasing at the same rate. So this is the spring snowmelt concentration of the wet year of the Trip 3 and the Maviculi Basin, and compared, this is the wet year compared to the dry year, is a little bit higher in the dry year. The summer base flow concentration kind of remains similar. And the total nutrient export we quantified here is 121 kilogram per kilometer square, in opposed to 23 kilogram per kilometer square of the watershed areas. So wet year has a lower concentration but higher export. And we are comparing to the Maviculi Basin, the wet year has a 54 kg per kilometer square, and compared to the dry year have only 16 kg per kilometer square. So the dry year has a higher concentration, but the dry year has a less nutrient export, and the wet year has a more nutrient export. We also look at the soil phosphorus, the Olsen phosphorus concentration, which was pretty high. We have collected the soil samples across the different locations. And we also look at the snowpack total for we collect the snow core and melt it and look at the total dissolved phosphorus. So snowpack phosphorus concentration is much lower than the what is inside the soil. So we believe that the soils in the north, in the Devils Lake basins, are a primary source of the phosphorus that is exporting to the channels and ultimately exporting to the lake. We also look at some of the hypothesize some of the contact opportunity, and in the wet year we detected that there's a basal ice layer form underneath our snowpack, and which kind of limit the snowmelt and the soil contact opportunity. That might be one of the reasons for the lower phosphorus concentration in the wet year. In the dry year, when this basal ice doesn't form and the soil is not as frozen as it is in the wet year, and that there is a more contact opportunity between the melt water and the soil itself when the water is exporting to the channels. We try to understand this again through a cold region hydrologic model for 2017 and 2018. We evaluated the model annual stream flow, model observed stream flow versus model stream flow for the Maviculi and the Trip 3 for 2 years. And also we have a snow water equivalent day. We also snow simulation evaluation, NSE of 0.75 for the Maviculi Basin of 2017 and NSE of 0.82 for the Maviculi Basin in the 2018 winter. Model also gave us the frozen soil area. It's in the 2017 frozen soil area. You see that both Trip 3 and Maviculi Basin are pretty much frozen till the stream flow started. And at that time, the entire water set started to defreeze, so particularly the basal ice removal and also defreezing the soil. And so as the stream flow is producing, there basically water is coming from on top of the basal ice layer or the frozen soil condition with the zero infiltration. So there is not much contact opportunity there. In contrast, in the wet years, the frozen soil area never got to 100%. It was a basically partial of the part of the water set was frozen. This is for the Trip 3 and the Maviculi Basin, and as you result, see that your melt runoff is only 3 millimeter here, is a 47 millimeter there. There is more opportunity to the melt to infiltrate and also in contact with the agricultural soil. Again, the similar phenomena here for the concentrations of and the stream flow relationship. With all these results, we kind of come up with a conceptual model with a wet year and dry year. And the wet year have a high SWE, high basal ice, high snowfall, high stream flow, with a low concentration and more nutrient export. And also the relationship with the concentration and the flow In the rising limb, we have a chemostatic condition. In the recession limb, we have a flushing condition. On the other hand, in the dry years, low sweep, basalized snowfall, stream flow with a less nutrient export with a high nutrient concentration. Again, here we see more of a flushing condition or positive relationship with that. I have few more slides on the Devils Lake in the lake water concentration. This is work from the Noah Galloway for his senior thesis work. We looked at the nitrate trend from the USGS data, concentration data for chains of lake from 1993 of 2021. These are the result of the man candle test. The blue triangle showing the upward trend, red triangle showing downward trend, and the white triangle shows no trend. As you see, the nitrate concentration is right in the rising in the Lake Arvin and Lake Alice, and we don't see any. And the McHugh Slough and the Lake Larita, they have a downward trend, but we don't see any trend over here. Total dissolved phosphorus trend. Again, the Lake Alice, Arvin has a higher the trend. The dissolved phosphorus concentration is rising, while the Lake Stump Lake and the Eastern Stump Lake area, there is a downward trend over there. We also try to model this nutrient export through a cold region water quality model. We have a kind of a physicochemical model where we take care of we have a process representation of denitrifications, plant uptake, the manure input, and the fertilizer input. That's true for nitrogen and the phosphorus as well. We have a refractory, labile, and those dissolved organic phosphorus all over there. And we started modeling the system. We have some preliminary result for the Mavekuli Basin. This is 27 winter uh, and a phosphorus export map throughout the Mavekuli Basin. This is the kg per kilometer square. In the preliminarily, we have a reasonable match with the observed TDP versus the model TDP at the more of a at the outlet scale, but we are still working on this model results. In conclusion, so I could say that massive flooding is due to the hydrologic change are the reason in the Devils Lake Basin. Dry winters results in the higher concentration and lesser nutrient load. Wet winter causes the lower nutrient concentration and the higher nutrient load. And the increasing trend of the nitrate and phosphorus in some of the chain of lakes, Lake Arvin and Lake Alice, are preliminarily being detected. Thank you. Any questions?
Okay, I don't think I saw any questions in the chat, but we can start here in the room if anyone had any questions. And then we can move to anyone online if they have any questions.
I guess I've got one.
Yeah.
How long does it take for the nutrients to move, say, from the, Lake Alice all the way to like the western outlet? What's the time frame for movement through the lake itself?
We haven't quantified that particular time frame to that for the movement. We are in the process of the lake modeling right now. Again, using the cold region hydrologic model, we embedded most of these processes inside the cold region hydrologic model, but it takes, I think, I don't have it right now exact number that how the transit time from the Lake Alice to the Lake Stump Lake.
Okay, and then I had a question. Did you look at any other chemical components to see if there's other correlations, or did you just look at those two to?
We looked at the dissolved nitrate and nitrogen, and also the and total nitrogen, and surprisingly in the Mavekuli Basin, the nitrogen concentration is way lower than the phosphorus concentration, and that is kind of consistent with some of the previous work by Greg Vanderberg in the same area. So that was, I think, one of the mystery right now. I don't know whether there's enough pools of the wetland causing the denitrification before water is going there, or there is any other nitrate sink there that is reducing the nitrogen concentration.
I was just gonna make a historical comment. Pete Pusk and I, 1987, did a study looking at the Spiritwood Devils Lake connection, trying to figure out how we could get more water into Devils Lake. So that's how much things have changed up there.
Right.
We also came in 1997, got caught in a blizzard, but we were drilling on the Talna Coulee because we had to find a mechanism where the state could put in the outlet and not end up in the court of the Hague because they couldn't violate international law. And we used pollen, primarily, trying to remember, it's Russian thistle, Salsola, as the marker. And so the state was able to go down to the depth, which was only, as it turns out, was I think less than 2 feet.
Okay, did we have any questions from anyone online? Anyone else in the room? Yeah, thanks for coming, Taufique. Did you have any closing remarks or?
I think for this new water center, we just established it, and we are looking for collaboration and cooperation across the state. I presented our skills and our expertise in the University of North Dakota. If you are interested to collaborate or interested to help us, please let me know. It will be great to have collaborate with across the state and with the hydrologist and learn from that. I think that this water center is committed to producing great science and also train the new generation of the water resources scientists and engineer, and also taking the message of water resources in the school and the colleges in North Dakota. Thank you.
Yeah, thank you. And keep up the good work, and it's great to see some names I recognize for the grad students and undergrad students, so that's nice.
I'm also glad to see that Joe Hartman's cleaned his office up a little bit.
Don't think he's in there.
No, he isn't, but
Needs a few more filing cabinets, I think.
Yeah, there's a couple of feet above him in the ceiling. All right, well, thanks again, and keep the good work.
Thank you. Bye.
Bye.
you say they're looking at the oaks.
Yeah,
Didn't you?
well, yeah, I agree with you.